Even though I've been teaching math for a long time, I'm always a little bit surprised when I see this again after not seeing it for a while. And I have to stop and remind myself for the reason why this is the case. Let's read this and hopefully you're going to understand what I mean. So we already know that the harmonic series, which is this one, the sum of 1 over n from 1 to infinity, diverges. And that was very simple to prove. You sort of compare it to an integral and you calculate the integral of 1 over x, right? The integral of 1 over x from 1 to infinity is infinite. And so the integral diverges, so the series also has to diverge because the series is even bigger than the integral. Sure. What's surprising to me is that if you make it alternating, and I call this the alternating harmonic series, it converges. So all of a sudden, even though the series itself, 1 over n, diverges, if you add this extra term that alternates between being positive and being negative, all of a sudden now the series itself converges. This is very surprising. I'll see if I can convince you that this is the truth, and that it is really the case. And so let's see how I'd go about doing that. So whenever I'm not sure about how to prove that a series converges or not, I'll take a look at its sequence of partial sums, and I'm going to go ahead and write a few. I'm going to write right here the odd terms of the sequence of partial sums first, and then the even terms next. So I'm going to, first of all, calculate S1. That is just A1. So that is just me plugging in n equals 1. Whenever I plug in n equals 1, the exponent of -1 here is going to be 0. So that's going to be 1 over 1. So it's just going to be 1 positive right here. Now when I calculate S2, this will be, now 2 is going to take the place of n. It's going to be A1 plus A2. A1 I already know is 1. But then A2 is going to be negative because now this exponent of -1 is going to become 1, making it -1. So this is minus 1/2. And then next I have S3. So I'm going to keep writing a few. As you can see, this is what you have. And S4 is going to be 1 minus 1/2 plus 1/3 minus 1/4. And then the next term, S5, will be, and then I'll do maybe just one more. And then I subtract the 1 over 4, and I add 1 over 5. And then S6, maybe the last one that I write, is going to be like this. So let's take a look at this carefully and see if we can get an idea of what's going on. Let's look at the odd ones and at the even ones separately. So if you take a look at this, here's what you can do. You can look at them in pairs like this. Maybe highlight it like this. What happens to these last two terms that you have? So these last two terms, you have -1/4. Let me maybe move it out of the way a little bit. So these last two terms give me a -1/4 and a +1/5. 1/4 is bigger than 1/5, so this overall is negative. Yes, this is negative. So that means, of course, that this term S5 is less than, so S5 is less than S3, right? Of course, right? Because we're adding, compared to S3, the only two terms missing are the ones that are in red over there. Didn't want my ruler there, sorry. Trying to find the pointer. Get the ruler out of the way. So the only two terms that you added are these two at the end. And so, and these are negative, which means S5 is less than S3. If you compare these two now S3 is less than S1, right? These two right here, again, if I move, these two are also negative. So what's going on? The sequence of the odd partial sums, they keep going down forever. Isn't that interesting? They keep going down forever. So as S progresses, I'm going to write 2n plus 1 like this to represent that we're only dealing with odd numbers. This is decreasing. This is decreasing. So this is interesting. Also, there is a bound to how low it's allowed to go. It's never allowed to go too low. If you stop to think about it for a second, they keep getting smaller and smaller, but could they keep getting smaller forever? Let's look at the other side and see if that can help us. Let's look at the other side. On the even ones, on the even terms, similar facts, similar characteristics can be seen here. Look at this. The S2s, this is positive. So S2 is definitely more than 0. It's definitely more than 0, positive. If you look at this, this is also positive. So S4 is more than S2, which was more than 0. And now these two are also positive. Why are they positive, right? 1/6 is smaller than 1/5, so subtracting them keeps it positive, right? Subtracting 1/6. So these are growing. So it seems like there's not a lot that you can do here. But now the trick is to compare the two sides to each other. So if you go and you compare, let's say S3, let's look at S3 here. S3 is easily comparable to S4 and S2. You can see that. When you compare S3 to S4, the only difference is this negative 1/4. So S4 is less than S3. S4 is less than S3. But also S3 is more than S2 because you're adding the 1/3. So what's going on here? If you just plot the sequence of partial sums, just plot them separately. What's going on? Let's just think of the odd ones first. Say 1. I'll skip the 2 and do 3, 5, 7, 9. Are these ever negative? Right? Look at these. Are they ever negative? Just think about it for a second. If you think and look at S3, let's look at it separately. There's a different way to see S3. S3 is 1 minus 1/2 plus 1/3. If you look at S3 this way now, this way now, this is the 1/2, which was your S2 plus 1/3. So this is a little bit bigger than S2. So it's still positive. Will S5 be positive? Will S5 be positive? S5 was 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, will that be positive? So let's look at it this way. Will that be positive? This is positive because 1/2 is less. This is positive because 1/4 is less. And this is positive. So 1s5 is also positive. You can keep this idea, keep following this idea. You're going to see that all odd s's are going to be positive. And they're decreasing, as you can see. So that means we're going down like this. And maybe you need a little bit of time to remind yourself of one of those theorems that we covered in a couple of videos ago. This is S2n plus 1. We already knew that it was decreasing. Now we already know. Now we also know that it is bounded from below, meaning it keeps going down, only the odd ones, and it converges to 0 because it's bounded below. Its infimum is 0. And that's the monotonic sequence theorem. You have a series that's decreasing. It's bounded from below, so it's gotta converge. You can do a similar argument with the odd one, with the even ones on this side. And the even ones are going to be coming from below and going to 0. They're going to be negative all the way, but they're going to go to 0. So they're the even ones, right? So they should be here. We're getting closer and closer to 0 also. So you have a sequence that, yes, it does alternate, but it gets closer and closer to 0 every time. So sometimes it's here, sometimes it's here, sometimes it's here, sometimes it's here. But you can see that it's getting closer and closer to 0 every time. I hope this was a little bit enlightening. I'm not sure that was the best explanation I could have mustered, but you can kind of see the idea. The sequence of partial sums converges, and that means then that the series also converges. So the alternating harmonic series converges, even though its fully positive variant diverges. So all of these ideas can be combined into another test called the alternating series test. And I'm going to read it over with you just under here. So here are the conditions that we need to check whenever you're given a series such as this. You need Bn. So Bn needs to be positive all the time. So 0 is fine a few times, as long as it doesn't keep changing. All of the changes in sign for your series needs to be confined to this -1 to certain power there. The series needs to be decreasing. The sequence needs to be decreasing. The sequence of the Bn's needs to be decreasing. And the Bn's need to go to 0. And if that's the case, then the exact same idea that we discussed just now for the alternating harmonic will also apply. And we'll have that the alternating series you're given is convergent. So the proof involves the monotonic sequence theorem for sure. I could have outlined it with epsilons and deltas, make it more convincing. But the idea, I think, is there. So from this point on, let's go ahead and make sure that we are able to use this theorem, the alternating series test, to solve for specific series and check them for convergence. So here's the series that I'd like to check with you, the examples that I prepared for today. Let me copy this. Let's start working. Let's work on A first. So A is, crop this for a second. So with this series for A, what are our Bn's here when compared to the alternating series test? You can see the alternating portion here, it's the same. So now we have to look at the bn's to be n squared over n cubed plus 1. So I have to check each of the two conditions. Is it true that bn is decreasing? So let me check. I need bn plus 1 to be less than or equal to bn. Of course, you can make it a function, take its derivative, and check that it's negative if that works for you. Other than that, you can also say that just set this equation with n, so you can say n plus 1 squared, n plus 1 cubed, plugging in n plus 1 into n, and then see if you can prove this, right? See if you can manipulate this inequality until you get to something that's obviously true. It's not going to be a walk in the park because you got to cube this, you got to square this, and likely you got to cross multiply things and cancel them out. I'm going to do it anyway, but it's not going to be exactly fun. This one you can cube. If you remember Pascal's triangle, it expands to this. And then I'm going to write one more line. I'm going to cross multiply this to get n squared plus 2n plus 1 times n cubed plus 1. You have to check that it's decreasing because all of the argumentation we did before relied on the fact that we could tell that one term was positive or the other term was negative because the terms we're alternating over were sort of smaller. So 1/5 is less than 1/4, so I can tell this thing is negative. So we need the decreasing part here. It is crucial. We can't throw it away. So these two are combined into a plus 2. I'm gonna multiply it all. I don't think I've done this enough in these videos, so I'm gonna do. This is why I'm doing it now. Just braving through. Canceling out what cancels out. N to the power 5 here, n to the power 5 here. Is there an n to the power 4 for me to cancel or something else? Hope it didn't miss anything. Can I combine anything on the left? It seems to be already combined. So let's move everything over to one of the sides. Let's move everything over to the positive side. So let's move everything over to the right side. Okay, so let's keep a 0. I have an n to the power 4 on that side. So that's n to the power 4. That I get to combine with this and this to get a 1 only, 1 n to the power 4. Let's look at the n's to the power cubed to the power 3. This and this, so I get 2n cubed. Let's look at the n's squared. So I get this and this, so it's 1n squared. Let's look now at negative 2n minus 1. So is this going to be positive at some point? Yes, it is. It is going to be positive at some point. And the reason why is because we have n to the power 4, n cubed, n squared, minus 2n plus 1. So at a certain point, this is going to be, n to the power 4 is going to be much bigger than double n. As soon as n to the power 4 wins this and beats this, so we're going to have that this is positive, which will mean, again, because I've only done legal reversible math operations, if I can make the bottom inequality true, I can also make the top inequality true. So I haven't proved that this is going to be decreasing all the time, but for series that doesn't matter. What matters is that it eventually becomes decreasing. So I can see that it is decreasing. Maybe I made a mistake somewhere here. I can't see it. If you do see it, let me know. I'm okay correcting those mistakes. I don't see them immediately as they are right now. Let me give it another look just to be safe. There should be 6 terms on the left. It seems fine, I think. Yeah, it seems fine. I don't even have to worry about these terms right here in the middle. N to the power 4 is enough for me to guarantee that I beat 2n plus 1, right? As soon as n equals 3 or something, starting from n equals 3, for example, n to the power 4 is going to be way bigger than 2n plus 1, and it's never going to catch up again. So it does take a little bit of work to prove that it is decreasing. Now I got to go and prove that the limit is 0. So the limit is 0. This is also necessary because if it isn't 0, then there's no chance that this thing converges because of the divergence test or the test for divergence. We need Bn to have limit of 0 either way. So n squared over n cubed plus 1. This is likewise divide by n cubed like this. Get limit n goes to infinity. So this is 0 over 1, which is 0. So we can say safely now that by the alternating series test, the series converges. And we had to check both things. We need decreasing and we need limit to be 0. So that's how it works. Let me go ahead and do the other example with you all. As I crop this, take a look at the second example. Do you think this converges, or do you think this diverges? It's a good idea to try and build intuition beforehand. I can immediately see that the bn's are 3n plus 1 over 2n minus 7, and that the limit of the bn's when n goes to infinity if I divide by n top and bottom, showing my work here, is going to be 3/2. Which is not 0. I said it equals 0, but it's not 0. It had to be 0 for the test for divergence, right? For the alternating series test, it had to be 0, but for the test for divergence, it also had to be 0. If this thing does not go to 0, there's no way that the whole general term of the series goes to 0, because all that this is doing, negative 1 to the power n here, is making it alternate. So there's no way that limit of an is 0. Right? I calculated the limit of bn, but an is negative 1 to the power something. Right? So the an's will be alternating between negative 3/2 and positive 3/2, and negative 3/2 and positive 3/2, which just makes it so that the limit is not equal to 0. And so the series diverges by the test for divergence. So I didn't have to go to the alternating series test. This is one of the advantages. Another interesting thing, let me finish what I was saying. One of the advantages of the alternating series test, because it allows you to not have to go to the other condition. If you check that the limit isn't 0 initially, you don't have to check for decreasing or increasing overall. Another important thing to check here is that see that the exponent of the -1 is not the same as it was before. Before I had -1 to the power n minus 1, and here I have -1 to the power n. That doesn't matter. All that this changes is whether the first term of my series is positive or negative, but the criteria are the same. So you can just change that, multiply by -1, evaluate convergence there, and then divide by -1 again. All you're saying when you're saying that a series converges or diverges is whether the limit is positive, limit exists or not of the sequence of partial sums. So I'm going to work on C. Video's getting a little long, so maybe I'll choose one and finish. Let me see. Is C now? C is nice. So I'm going to talk to you about both of these fairly quickly and let you work on these yourself. So I'm not going to solve these problems all the way through because the video is getting a little too long. Now look at this. For C, your Bn is the sine of pi over n. You can see from the unit circle that this is decreasing, but also it's easy to prove if you take f of x equals sine pi over x and take its derivative. F of x is going to be derivative of the outside function times the derivative of the inside function. Chain rule, right? So this is going to be negative pi x to the power -2, like this. So this is negative cosine pi over x, maybe a pi multiplying outside divided by x squared. So you can see that this is positive all the time, pi is positive all the time, and the cosine is going to be positive, but the derivative, I forgot the prime here. As long as the angle is in the first quadrant, making the cosine positive, so starting from x greater than 2, making this pi over 2, right? Exactly at x equals to 2, this is the cosine of 90 degrees, which is 0, but after that, your angle is going to be in the first quadrant, so the cosine of the angle is going to be positive. And so dividing by the angle squared, multiplying by pi, all stays positive, but this one final negative sign makes your entire series, your Bn's, decreasing, right? On the other hand, the limit of Bn when n goes to infinity is the limit of sine pi over n goes to infinity, which is the sine of 0, which is 0. So both conditions apply for C. And so you have that by the alternating series test, the series converges. I said I wasn't going to do it all the way through. I ended up doing it because it was kind of an interesting problem to deal with in terms of derivatives. And that way you've seen two different examples, one where I showed decreasing by solving an inequality and one where I showed decreasing by using the derivative. So it's up to you what to do. Let me do D as well now. I think D is also convergent. D kind of looks like a telescoping series if you take a look at it. If you exclude the alternation portion, you can kind of see that you'd be adding, what would you be adding? Root 2 minus root 1 plus root 3 minus root 2 plus root 4 minus root 3. And so these would cancel. These would cancel. But you can see that the last term always includes plus a root of something big. So without the alternation, I would think this diverges. If I were to see this as an alternating series, I would think that this diverges without an alternating series. Sorry, let me go back and say it again. Without this alternating term, I think this diverges. So this is my opinion, but you can double check. But if you add this now, now you have your bn's, n plus 1 minus root n. All you have to check is whether they're decreasing and whether the series itself has a limit of, the sequence itself has a limit of 0. So limit of bn needs to be 0 and the bn's need to be decreasing. So I'm going to go ahead and do a thing. I'm going to multiply this top and bottom by the conjugate like this. And then you can see that bn equals n plus 1 minus n, like this. So you can see that's just 1 over n plus 1 plus root n. So as n increases, there's no question that the bottom of this fraction is growing. You're adding two roots that are getting bigger and bigger because n is growing. And so bn is clearly decreasing. I won't even have you on a test or an exam or something prove this. Whenever you have a constant at the top and something at the bottom that's obviously growing, or even vice versa, something at the bottom that's obviously decreasing, right? I won't have you prove, I'll only have you prove whether a sequence is decreasing when you don't have constants involved, when both top and the bottom of the fraction are changing over time. So you should check with your teacher whether this is what they want if you're watching this and you're not one of my students. Now, I know it's decreasing. I got to check that the limit is 0. Is the limit of this 0? Of course, right? Just same reason, because this is constant and this is changing. I haven't changed bn, right? This is the same bn I had before. I multiplied by 1 top and bottom, right? Sorry, I multiplied by the same number top and bottom, which is equivalent to multiplying by 1. Sorry, I'm a little sleepy. This is too early in the morning for me. And so by the alternating series test, this series converges. Now, very, very interesting. The alternating series test cannot tell you that a series diverges, only that it converges if both conditions are satisfied. If you go back a little bit to the theorem, if this condition fails, then for sure you know that the series diverges if the second condition fails. But if the second condition is satisfied, but the first one fails, if the first one fails, then you don't know. So the test is kind of inconclusive in that way. You're not really sure whether the series is going to converge or diverge if the limit of the bn's is 0, but the series is not decreasing. So we're going to have to come up with other alternatives. Video ended up a little longer than what I wanted, but I hope it was clarifying. Sorry for misspeaking too many times.